So hello friends, welcome to channel Learning Chemistry. So today we will talk about the previous year solution on the anomeric effect and the conceptual approaches. Okay, so let's start our topic. So this question have previously appeared in 2017 December in CSIR NET. This is acetyl linkage. So there are two stereocenter. Here is a methyl. So and there is another hydroxy group. So there is four types of possible orientations or conformations of this acetyl hydroxy acetyl. So we have to choose the correct conformation out of that. So let's think about the linkage. So if you write this acetyl linkage, the main 6-member skeleton, so there will be 2 oxygen in the ring. Okay, let's first talk about the what will be the possible orientation of the methyl. So if the methyl is placed in the axial position, so there are two opposing phenomena. One, you know that from the anomeric effect there is a lone pair of this oxygen, so that could be donated to the sigma star of this CC bond. Okay, so from this non-bonded orbital, the lone pair can be donated to the sigma star of this CC bond. So that could be a stabilizing factor, but again there will be some destabilizing factor, because if the methyl is placed in the axial position, there will be some 1,3 diaxial interactions with these neighboring hydrogens from these methyl hydrogens. So these are the two opposing factors. So here what happens that as the electron, as you can, if you watch my video on anomeric effect, you can get a conceptual understanding that if this methyl, if this methyl have significantly electronegative character, then this electron donation from this non-bonding orbital to this CC or any CX antibonding or the sigma star orbital donation will be favored if the electronegativity is sufficiently higher. But methyl group have no electronegative, have neither such high electronegative effect. So this donation to the antibonding orbital of CC bond will be not much favored. Okay, so this stabilizing factor will be not much there, and the destabilizing factor due to the 1,3 diaxial strain will be higher. So the methyl group likes to stay in the equatorial position. So these two options are eliminated where the methyl groups are in axial. So answer will be from 1 and 2. So let's think about this OH group, the position of this OH group. So again, now let's take our consideration to OH group. So what will be the possible orientation from the OH group? So if you think that, you know that from the normal understanding of conformation, that if a polar group resides in the equatorial position, then the polar group, you know that the solvent, if it is placed in the polar solvents, then the polar solvent aggregates around this polar group due to the some interactions, due to the lone pair of the oxygen or due to hydrogen bonding, anything. Okay, so the steric volume of this group increases. If the steric volume of this group increases, then if it is placed in the axial position, then that faces severe 1,3 axial strain from the axial positions. Okay, so the polar group like the OH or any other like ester or ketones or any polar group, due to this aggregation of solvent molecules, polar solvent molecules on the around this polar group increases. So those groups will loves to stay in the equatorial position. But here you can see that if the corresponding those points from where the 1,3 diaxial interaction could be generated, there is oxygen. So there is no such hydrogen or any group which can exert the 1,3 diaxial strain. Okay, so there are oxygen and that have just a lone pairs. So there is nothing to interfere with this oxygen group in the axial position. Okay, so there could be a possible reason that the OH group will like to stay in the axial position, but there is some another stabilizing effect also. So if you closely look that there is a hydrogen, okay, so if this sigma bonded electron density can be donated to the sigma star of this CO bond. I am not saying that this phenomena will be very prominent, but there will be some stabilization due to this, because OH group oxygen is electronegative, so the sigma and sigma star overlap is there. This stabilizing fact can dictate the position of this axial OH to the axial position, and nevertheless, and again, due to this position of this oxygen in these states, there is no 1,3 diaxial strain. 1,3 diaxial strain is absent here. So both these facts helps the OH group to remain in the axial position. Okay, so due to this fact, this OH group stays in the axial position, and the methyl group, as due to the 1,3 diaxial strain, that doesn't want to stay in the axial position, and also as the electronegativity of methyl group is very much less than the OH group, then this back donation from the non-bonded or any electron donation to the CC or any CX sigma star orbital will be much less favored. Okay, so due to this reason, the methyl group likes to stay on the equatorial position, and OH group likes to stay on the axial position. Okay, so this is our correct answer, which is 1. So you have to remember that because there is no 1,3 diaxial strain, the OH group likes to stay in the axial position. But if there is a simple cyclohexane chair, then the equatorial OH conformation will be predominant, because there is 1,3 diaxial strain involved, and due to the polar, and in the polar reaction medium or any solvent medium, the steric volume around this group will be much higher. Okay, so you can write that in polar, the equatorial oxygen conformal will be much higher than the axial OH conformal. Okay, because there will be steric volume, as I said, that will be higher, and that will interact with these axial hydrogens. But in non-polar medium also, the equatorial OH group have upper hand than the axial OH. Okay, but the percentage of axial OH will be increased. Okay, so there is a lot of concept behind this question. There is a small question which can be attributed to the anomeric effect. And anomeric effect does you don't need to think that anomeric effect only belongs to the carbohydrate chemistry. It has many effects in everywhere in organic chemistry. Okay, so let's get back to next question. So you know that this question you have faced previously many times in your board exams, in your MSc or BSc. So you know that there is 2 types of compounds has been given. So let's first talk about this Newman projection. So here you can see that from this conformer there will be hydrogen bonding. You have to look after that, and you have to minimize the steric repulsion, the Gauss-Butane interaction. So those conformers you have to select where the hydrogen bonding is favored and this repulsion will not be there. Okay, so let's find it. So here is a repulsion is there, so this will be not our target, and also hydrogen bonding is not there. So here hydrogen bonding is there, and also this methyl groups are anti to each other, so you can take this in consideration. So here you can see that there is a hydrogen bonding is present, but there is a repulsion is there, so this you cannot take into the consideration. So here you can see that there is again hydrogen bonding is there, and methyl are also opposite and anti to each other, so you can take this example and this example into your consideration. But there is another complex which you have to take care of, you have to explain. So here you can see that there is a 2 electronegative fluorine atom is positioned 2 carbon respectively. Okay, both the negatively polarized atoms are 60 degree apart to each other. There could be a severe lone pair or the dipole repulsion, so that could be least stable, but that not the case. the actual stabilization comes from the somewhere else. So let's try to find that. So if I can extend this Newman in Sawhorse, so that will be easy to discuss. So if I write this structure in this form, so here this is the NT2 flow into each other, so there is no such, sorry, I have to write another structure to explain it. Okay, so here you can see that the fluorine, both the fluorines are 60 degree apart. Okay, so here is one thing present, as the CF, the fluorine, have very high electronegative as that of the carbon, so this bond is very much polarized. Okay, so the sigma star orbital energy will be very much less. So the donation from this sigma star of this CH bond from this sigma star orbital will be very much favored. There is an electron donation from the sigma to the sigma star of CF will be very much favored if they are NT to each other, the CF bond and CH bond. So then will be the orbital overlap will be maximized. Okay, so for that reason both the fluorine have to be 60 degree apart to each other, so that there is, if they are 60 degree apart to each other, then for each fluorine there will be one hydrogen NT to them, so that can stabilize the system and reduce the energy. Okay, you can understand. You can also explain this in terms of resonance. So this is the molecular orbital explanation, but I am not a big fan of resonance or any kind of explanation here, because molecular orbital explanation explains the best. So here I am again writing that if this sigma star orbital and this sigma orbital are perfectly oriented at the NT to each other, then the donation from sigma to sigma star will be favored, so that will stabilize the whole system. So if the fluorines are 60 degree apart to each other, then this type of interaction will be favored, and that will stabilize the system, and that overcomes the dipole or any kind of polar dipole repulsion, because that repulsion will be minimized after this type of electron donation. Okay, so we have to take this as our answer. So here both the conformations are perfectly, because there is one hydrogen NT to this fluorine and one hydrogen NT to this fluorine, that can stabilize the system very good. Okay, so this is our overall correct answer. So that is also types of the orbital interaction are kinds of similar to the anomeric effect. What is the main reason driving to the anomeric effect? So I have discussed it here. So now this question have previously came in CSIR NET in 2019. So here is a question asked, for the which of the following the conformer B will be more stable than A. So you have basic knowledge that if the conformations are placed in the equatorial position, that is mostly stabilized than their axial form. So here is the diequatorial form, and you have the basic knowledge is that the diequatorial form is much stabilized than the diaxial form. But due to some other reasons, there could be the diaxial form could be the more stable than the diequatorial form. So what could be the reason? So again you have to get to the molecular orbital explanations here. So if the axial groups which are R could be some interactions with this hydrogen NT to them, so there is some sigma bond, the CH bond. So if this sigma donation can be donated to the sigma star of these CR bonds, so then some stabilization effect can be operated, which can stabilize in spite of the axial orientation of this R group, because there could be 1,3 axial interactions there. Okay, so for which of the following molecules this sigma to sigma star donation will be favored? I have previously explained that the sigma is for the donation, the sigma star orbital, you know that from the molecular orbital diagram, the sigma star orbital have the highest energy for any bond. Okay, the sigma star orbital have the highest energy. So if you can decrease this energy of the sigma star orbital, then this donation from sigma to sigma star orbital can be possible. So that only can be possible by the electronegativity effect. So if the electronegativity effect of this R group is sufficiently high, then the energy of the sigma star orbital can be lowered, and then this donation from the sigma to sigma star orbital can be favored. So here the most electronegative is the fluorine. So if there is a diaxial fluorine is there, so there is very good donation from this anti-CH. There is this from the sigma orbital of this CH bond that could be donated to the sigma star of CF bond, because due to the high electronegativity of CF, the sigma star orbital energy of the CF is very low, so the donation is favored. Okay, so only then for the fluorine, the B conformer will be much more stable than the diaquatorial conformer, because in the diaquatorial conformer there is no such kind of donation from sigma to sigma star will be there. And you know that the fluorine have, among these four groups, the fluorine have the much less size than any of this group. So due to the lesser size, the 1,3 diaxial strain also is less operative from the fluorine because of its axial position. Okay, that also favors the fluorine to remain at its axial position. So both steric and electronic, both the effects favors the fluorine to gain its axial position. Okay, so in respective of size, fluorine have least size, more or less. Fluorine have least size than the OMe, then the Me, then the Cl. More or less this is the size, but fluorine has the least size, that is confirmed. Okay, so that lowers actually the 1,3 diaxial strain. Okay, so both these reason the fluorine resides in the axial position. So let's move on to our next question. So in this problem, the whole problem I will not discuss here, but I have to discuss a significant thing, which is that here you can see that there is oxygen and acetate in the axial position. So that actually greatly facilitates the removal of the acetate, because this lone pair and if the acetate has significantly high electronegativity, so this lone pair can be easily donated to the sigma star orbital of this CO bond. So I can write again here. So this lone pair can be easily donated to this sigma star orbital of this CO bond, because that has very much electronegativity that can facilitate this sigma star electron donation. Okay, so that just facilitates the removal of acetate, and after that the usual reactions, the lone pair of phosphorus from PbR3 attacks here, and again it just removes. Okay, so that is a different scenario, but here this anomeric effect non-bonded to the sigma star, the phenomena, that bonding aspect is also operated in the reactions also. So that is my main point, and targeting this problem, that is the main idea of my inclusion of this problem here. Okay, so this type of orbital interactions also participate in the reactions also. Okay, so I am concluding my video here. So next I will come up with a similar video, that this from the NMR delta value or NMR value you can also clarify that this type of interactions are operating actually. Okay, so I will make a separate video on that. That will be a very conceptual video. So keep listening to Learning Chemistry. Thank you.